Another day, another story. Deep learning is a subset of machine learning, which itself is a subset of artificial intelligence, AI. It involves using neural networks with many layers, hence, deep, to model and understand complex patterns in large amounts of data. Here's an overview of key concepts and applications of deep learning. Welcome to Tabo Eminent Channel. Key concepts. Neural networks. The core of deep learning, inspired by the human brain, consists of interconnected nodes or neurons. Activation functions. Functions like ReLU, rectified linear unit, sigmoid, and 10H introduce nonlinearity, enabling the network to learn complex patterns. Training involves using a dataset to adjust the weights of the neural network through a process called backpropagation, where the error is propagated back through the network to update the weights. Loss function measures the difference between the predicted output and the actual output. Common loss functions include mean squared error, MSE, for regression and cross-entropy loss for classification. Optimization algorithms. Techniques like gradient descent or more advanced versions like ADAM are used to minimize the loss function. Popular architectures. Convolutional neural networks, CNNs, primarily used for image and video processing. They utilize convolutional layers to capture spatial hierarchies in data. Recurrent neural networks, RNNs, ideal for sequential data like time series or natural language. Long short-term memory, LSTM, and gated recurrent units, GRUS, are popular RNN variants designed to capture long-term dependencies. Generative adversarial networks, GANs, consist of two networks, a generator and a discriminator, that work against each other to produce realistic synthetic data. Transformers, primarily used in natural language processing, NLP, they utilize self-attention mechanisms to handle sequential data more efficiently than RNNs. The evolution of deep learning. Early beginnings. The journey of deep learning dates back to the 1940s and 1950s, with the development of artificial neural networks. Warren McCulloch and Walter Pitts proposed the first conceptual model of a neuron in 1943, inspired by biological neural networks. This early model laid the groundwork for future developments but was limited by the computational resources and theoretical understanding of the time. The perceptron. In 1958, Frank Rosenblatt introduced the perceptron, an algorithm for supervised learning of binary classifiers. The perceptron was a simple neural network with an input layer and an output layer, capable of solving linearly separable problems. Despite its limitations, the perceptron was a significant milestone, demonstrating the potential of neural networks. The AI winter. However, the enthusiasm for neural networks waned in the 1970s, a period known as the AI winter, due to the limitations highlighted by Marvin Minsky and Seymour Papert in their book Perceptrons. They pointed out that the perceptron couldn't solve certain types of problems, such as the XOR problem, leading to decreased funding and interest in neural network research. Resurgence with backpropagation. The 1980s saw a resurgence of interest in neural networks, largely due to the development of the backpropagation algorithm. Geoffrey Hinton, David Rumelhart, and Ronald Williams popularized this technique, which allowed for the efficient training of multi-layer neural networks. Backpropagation addressed many of the limitations of earlier models and enabled more complex neural networks, paving the way for deep learning. The rise of deep learning. Big data and GPUs. The 2000s and 2010s marked the true rise of deep learning, driven by the availability of large datasets, big data, and advancements in hardware, particularly graphics processing units, GPUs. GPUs, originally designed for rendering graphics, turned out to be well suited for the parallel processing required by neural networks. Breakthroughs in computer vision and NLP. In 2012, a deep convolutional neural network, CNN, called AlexNet, developed by Alex Krzyzewski, Ilya Sutskever, and Geoffrey Hinton, won the ImageNet Large-Scale Visual Recognition Challenge, ILS-VRC, by a significant margin. This victory demonstrated the power of deep learning in computer vision and sparked widespread interest and investment in the field. Simultaneously, deep learning was making strides in natural language processing, NLP. In 2014, the introduction of the sequence-to-sequence, seq-to-seq, model by Google researchers showed how RNNs could be used for tasks like machine translation. Later, the development of the transformer model in 2017 revolutionized NLP, leading to powerful models like BERT and GPT. Real-world applications. Healthcare. Deep learning has transformed healthcare by enabling advanced diagnostic tools. For example, Google's DeepMind developed a deep learning system that can diagnose over 50 eye diseases with accuracy comparable to human experts. Additionally, deep learning models are used for predicting patient outcomes, personalizing treatments, and accelerating drug discovery. Autonomous vehicles. Companies like Tesla and Waymo are leveraging deep learning for self-driving cars. Deep learning algorithms process data from sensors and cameras to detect objects, predict their movement, and make driving decisions in real time. These systems aim to reduce accidents and improve transportation efficiency. Finance. In finance, deep learning models are used for fraud detection, risk management, and algorithmic trading. For instance, J.P. Morgan Chase developed a model called COIN, Contract Intelligence, which processes legal documents and extracts important data, significantly reducing the time and cost associated with document review. Entertainment. Deep learning has revolutionized content recommendation systems used by platforms like Netflix and Spotify. By analyzing user behavior and preferences, these models provide personalized recommendations, enhancing user engagement and satisfaction. Challenges and future directions. Interpretability and transparency. One of the main challenges in deep learning is the interpretability of models. Often referred to as black boxes, deep learning models can make accurate predictions without providing clear explanations. This lack of transparency can be problematic, especially in critical applications like healthcare and finance. Data and computational resources. Deep learning models require vast amounts of data and computational power. While big data is increasingly available, managing and processing this data remains a challenge. Moreover, training deep learning models can be time-consuming and expensive, necessitating specialized hardware and infrastructure. Ethical considerations. As deep learning becomes more integrated into society, ethical considerations around bias, privacy, and job displacement become crucial. Ensuring that models are fair, transparent, and respect user privacy is essential for building trust and avoiding negative societal impacts. The future of deep learning. Looking ahead, deep learning is poised to continue transforming industries and driving innovation. Advances in areas like unsupervised learning, reinforcement learning, and neuromorphic computing could further expand the capabilities and applications of deep learning. Moreover, interdisciplinary research combining deep learning with fields like neuroscience and quantum computing holds the potential for groundbreaking discoveries. In summary, deep learning has come a long way from its early beginnings to becoming a cornerstone of modern AI. Its impact is felt across various domains, driving innovation and improving lives. As we continue to advance, addressing the challenges and ethical considerations will be key to unlocking the full potential of deep learning. Thanks for watching. Request you to subscribe the channel.